Hello, I have about 30 minutes till I have to leave for my only class of the day, and I actually have my final for this class uh, this evening at 6:30. So I'm doing a little extra practice, and that involves recording. So we are going through the fall 2017 final from a 266, only doing the bits that are applicable for the first midterm. Question 1, identify the differential equation corresponding to the direction field below. So we see that there are 2 points of stability. We have a semi-stable point at 2, where anywhere above 2 will tend down towards 2, and anything below 2 will tend down towards 0, which is a stable point. So what we're going to be looking for is this kind of behavior in one of these points. Let's take a look at some of these answer choices. So A, if we draw out 0, 2, above 2, below 2. Let's see, if we're below 0, for A, we're going to have a positive slope because this will evaluate to a positive number. If we are at 1, we're going to have a negative slope. And if we are at, let's say, 3, we're also going to have a negative slope. And so A, as it turns out, is a little anticlimactic, but this has the exact behavior that we're looking for. A is correct for number 1. 2, let y of t be the solution to this initial value problem given here. So a very clear case where, it's time to do some integrating factor. Let's rewrite this dy dt plus 2 over t y is equal to sine t over t. Here's our function q, here's our function p. Our function rho, our integrating factor, is going to be e to the integral 2 over t dt, which is 2 ln t to ln t, and overall this simplifies down to t squared. So now we can set up our solution as y of t is equal to 1 over rho, so 1 over t squared, times the integral of q of t, sine t over t, multiplied by rho of t squared dt. So we will cancel here. We have, I'll just get rid of that. That got really small. We have t sine t. That integral right there, we're going to have to do some integration by parts. So let's see, u is equal to t, du is equal to 1 dt, dv is equal to sine t, and v is equal to negative cosine t. And so this will simplify down to 1 over t squared times uv, so negative t cosine t, minus the integral of v du, so negative cosine t dt. These two will cancel out. The integral of cosine is sine, so we have plus sine t plus c. And all of this is equal to y of t. Okay, let's see if we can evaluate this using our initial condition and actually get a correct answer out in the end. So we're given that y at pi is equal to 0, so 0 is 1 over pi squared times negative pi, and then the cosine of pi is negative 1, plus the sine of pi, which is 0, plus 0 plus c. So overall, simplifying things down in here, we have pi plus c. And the only thing that this can be, so that it evaluates to 0, the only value that c can have is negative pi, like so. So hopefully we can go in here, replace our c with negative pi, and evaluate this thing at 2 pi and get an actual get an actual number out. So evaluating at 2 pi, I'm going to go up here and don't have much space to work with. 1 over 4 pi squared times the quantity negative 2 pi times the cosine of 2 pi, which is 1, plus the sine of 2 pi, which is 0, minus pi. So that's negative 3 pi. And so overall, we get negative 3 pi over 4 pi squared, which is negative 3 over 4 pi. And so C is our correct answer for 2. 3, let's find the solution to this initial value problem. Well, this is clearly a separable equation. We're going to multiply y over. We'll have dy dx times y is 1 minus 2x. We'll multiply the dx over dx. And we are already ready to integrate. So integrate both sides. We will get y squared over 2 is equal to x minus x squared plus c. And we're told to give things in explicit form. So we will see that C, option C, is definitely not an explicit form. I'm kind of jumping around a little bit, but we can directly rule that one out. Let's figure out what this looks like in explicit form. So let's multiply everything by 2. Y squared is equal to 2x minus 2x squared plus a different constant C, and then taking a square root. Y is equal to plus or minus the square root of 2x minus 2x squared plus c. So now looking to our initial condition, in order for y of 1 to be negative 2, we're going to have to use the negative side of the square root. So negative 2 is equal to negative root 2 minus 2 plus, well, what would this have to be? This would have to be plus 4 in order for this to evaluate to negative 2. So knowing that, we can replace our c with plus 4, and we have our answer, which is answer choice D. Initially, a tank contains 500 liters of pure water, blah, 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 blah. We're gonna go through all this anyway in a second, because we know that our equation for this kind of thing, when we have some solute entering a tank and then either leaving the tank at the same rate or a different rate, we need to use the equation dq dt plus r0 over v of t q equals ri ci. So r0 in this case is the rate of outflow from the tank, and it says that that's 1 liter per minute. The rate of inflow is 2 liters per minute. Let's see, V of T is going to be our initial volume, so 500. And then each second we have 2 liters flowing in, 1 liter flowing out. So plus T, we want that to increase by 1 unit for every unit T. Let's see, which numbers am I missing? Oh, CI, that's our concentration of the solute in our inflow, which is 0.3. So we should have everything that we need to set this up. dq dt plus r0, which is 1 over 500 plus t multiplied by q is equal to RICI 0.6. So looking to our answer choices, we'll see if we take this term, subtract it over to this side, we're left with exactly option C, and they don't make us solve it, which is kind of a blessing. Don't really want to go through that. Okay. 5. Although I'll note, if we were to solve it, we would use integrating factor, like we always do with these. 5. Use Euler's method with h equals 0.5 to approximate y of 1 when we're given this expression for y prime. So we know that y of 0 is equal to 2, so y of 0.5 we can approximate as y of 0, so 2 plus 0.5 times our slope, our derivative here, y prime, evaluated at y of 0 equals 2. So that would be y prime is equal to y, which is 2 times 1 minus 0 times 2. That's just going to give us 2 plus 1/2 times 2, which is just 3. So now we have a new approximation. Y at 0.5 is approximately equal to 3, and we can use this to approximate y of 1. That's going to be approximately y at 0.5 plus 0.5, our step size, multiplied by this guy again, but evaluated at our new condition here, which will be 3 times 1 minus 0.5 times 3. And this will be 3 plus 1/2 times 3, so 3 over 2 times 1 minus 1.5, so negative 0.5, negative 1 over 2. This will give us negative 3 over 4, and 3 plus negative 3 over 4 is 2.25, and our answer for 5 is B. So just remember, the formula that we're using here is that y at n plus 1 is approximately equal to y at n plus h, our step size, multiplied by y prime evaluated at n. And if you just do that a couple times, you should be good. Question 6, which of the following is an implicit solution to this initial value problem? Immediately, the exact differential equation sirens should be going off in your head. They're never going to make you integrate anything like this in using substitution or anything like that. This, just by looking at it, has to be exact, but we have to show it. So if this is a function m, and this is a function n, then my must be equal to nx. And if this is true, then our equation is exact. My is the partial derivative of m with respect to y. That will give us e to the x cosine y minus 2 cosine x. And let's see if that's equal to nx. Well, nx is going to be e to the x cosine y minus 2 cosine x. So it's true. So our differential equation here is exact. So all we have to do is take the integral of m dy and compare it with the integral of n. Sorry, I said dy here, didn't I? dx and n dy. There we go. So the integral of m dx is e to the x sine x minus 2y sine x plus x cubed over 3. And then on the other side, e to the x, this is a y, isn't it? E to the x sine y minus 2y sine x plus e to the y. So we see that we have overlap in these terms here, but we have terms that are only occurring on one side of things. So remember, we only count the overlapping terms once, and then we're just going to tack on the other two. So overall, our equation is e to the x sine y minus 2y sine x plus x cubed over 3 plus e to the y is equal to some constant c. And if we look around, we see that d is the only one that matches all of these terms. And if we evaluate y of 0 equals 0, we will get 0 minus 0 plus 1 equals c. So there's where they're getting the c equals 1 term. So 6, our answer is D. Let's find the solution to this initial value problem. Right here, we can make a characteristic equation. R squared plus R minus 6 is equal to 0. This is R plus 3, R minus 2. So R is equal to negative 3. R is equal to 2. And so we can set up our solution. Y of t, it looks like they're using, is C1 e to the negative 3t plus C2 e to the 2t. And we'll also have to take y prime of t, and that will be negative 3 c1 e to the negative 3t plus 2c2 e to the 2t. Okay, fine. We can now use these two initial conditions that were given to do some linear algebra and get ourselves some values for C1 and C2. So plugging in y at 0 equals 0, we have 0 equals C1 plus C2, because all of our e terms will go to 1. And then we have 5 is equal to negative 3C1 plus 2C2. Let's make a matrix out of this. We have, it's an augmented matrix of 1, 1, 0, negative 3, 2, 5, where our solutions are over here. Let's add 3 row 1s to row 2. We'll get 0, 5, 5. This can simplify down to 1, 1. Subtract here, we'll get 0, negative 1. And so all that's telling us is that C1 must be negative 1, and C2 must be 1, so that both of these cases up here are true. Let's see what answer choice corresponds with this. That looks like it's answer choice C. So 7 is in fact C. Question 8, which of the following is the largest integral? I said that the other take too. Interval in which the solution to the initial value problem given below is guaranteed to exist by the theorem of existence and uniqueness. So first thing you want to do whenever doing these problems is divide things out so that your highest term here, which in our case is y double prime, is sitting by itself. So y double prime plus sine t over t squared minus 1 y prime minus 1 over t minus 3 t squared minus 1 y is equal to e to the t ln t over t squared minus 1. All three of these terms here have to be defined, have to be continuous for our function to be defined within a certain rectangle. So we see that we're given a condition here for y at 2. So we're looking for the furthest we can go in either direction from 2 without hitting some point where we're discontinuous. And we'll see that we have a discontinuity when t equals plus or minus 1, when t equals 3, and when t is less than 0. That's coming from our ln t up here, and I'm getting these other two conditions from that term and that term, respectively. So if we're starting at 2, the first value we're going to hit in the left direction that's no good is going to be 1, and then on the other side we're going to hit 3, and so we can only prove that a solution to this initial value problem is guaranteed to exist on this pretty small interval right here, because anything more and we'll be dealing with some discontinuity. So 8 is D. 9, our last question. y1 equals e to the x is the solution to this second order differential equation. We're going to do some reduction of order. First off, let's take y double prime and put it by itself. So y double prime plus 2 minus 2x over x, y prime plus 2 minus, or sorry, x minus 2, y is equal to 0. So there's a nice equation that we can use for reduction of order so that we don't have to go through all of the yucky motions that they want us to do with substitution. That says that y2 of x is equal to y1 of x multiplied by the integral. Oh, there's a tour group going by right outside the room I'm recording in. That's great. Times the integral. We need a really big integral because we have e to the negative integral of p of x, where p of x is the term on y prime. P of x dx, all divided by y1 of x squared dx. Okay, so it's pretty big, but it's actually a big time saver in the end. So this y1 here and here is going to be our first solution, which we know to be e to the x. So I'll replace it. E to the x, e to the 2x, and then we're going to need the negative integral of p of x. That's going to be, let's see, the negative integral of this term right here is what we said, which is 2 minus 2x over x. We can split this up as 2 over x minus 2 dx. I'm going to put this, distribute this negative sign in. There we go. And this integral will give us negative 2 ln x plus 2x. Plus 2x. Okay, so we can go substitute that in. Negative 2 ln x plus 2x. Okay, gonna make some more room down here. Let's see. Let's split this off. We know that we can take this plus 2x in the exponent and change that into an e to the 2x. These two are going to cancel, and all we are left with is e to the negative 2 ln x, which is the same thing as x to the negative 2 dx. So you can kind of see how for a little bit there we did have a really scary integral, but things have calmed down since. And since we're looking for v of x, which is the term that's multiplied by e to the x to give us y2, really all we're looking for is v of x there. And this integral is going to give us negative 1 over, well, negative x to the negative 1. Okay, and importantly, it's important to recognize that because our solutions can be any linear combination of these two solutions, it doesn't matter whether we have a plus or a minus here, because the constant that we're multiplying this solution by could very well be negative. So then it's fair to say that plus x to the negative 1 is also a valid solution. So B is our answer. B is our answer for 9. And that is actually it. I can't do any more of these problems. And I hope that was helpful. I'm a little unhappy with my explanation of this last one, though. I hope you got the gist. But anyway, I'm going to go to class now.